Check it out now, y'all.
nanoHUB-U, online instruction.
So welcome to Lecture 5 in this first week of courses on the fundamentals of AFM. In this first week of lectures, we're basically trying to systematically work our way through all the interaction forces that might arise between a tip and a substrate. The approach we've chosen to follow is we're first considering relevant forces between ions and molecules. Since tips and substrates are comprised of atoms and molecules, we're going to have to integrate these interactions we've been discussing over the shape of a tip and over the shape of a substrate in order to get tip-substrate interactions. That will come in week 2 of the class. But for now, we're still systematically trying to understand the forces between relevant atoms and molecules. So today we're going to focus on even more subtle interaction forces than we've already discussed. And in particular, we're going to focus on the Keesom force and the Debye force. We're going to derive those expressions for you and try to lead up to them in a systematic fashion. So the last lecture, we discussed four interaction forces. The diagram here indicates those four forces that four interaction potential energies that we actually discussed. I'm starting to label the cases now because we're starting to get a significant number of these cases, and so the number associated with each bubble should allow you to go back and find the relevant slides, which are also numbered accordingly to match this diagram. So cases 1, 2, 3, and 4 were discussed in the previous lecture. In this particular lecture, it's going to just get more complicated because now we're going to start to consider how molecules interact with other molecules. We're no longer concerned with ions interacting with molecules. We're more interested now in polar molecules interacting with polar and nonpolar molecules. This will give rise to something called the Keesom and Debye forces, and those two forces will be derived in this particular lecture. In the next lecture, we're going to discuss the London force, which is the weakest force of interaction that we'll discuss. So as a rule of thumb, roughly the ratio of the Keesom to the Debye to the London interaction potential energies, roughly those are in the ratio of 100 to 10 to 1, with the Keesom force being the dominant of the three. This is a difficult lecture to follow, a lot of details. I'll try my best to explain the slides in a logical fashion. So to begin with, we're going to consider how a polar molecule interacts with a polar molecule, and we're going to write down expressions for that interaction, and we're going to do it for two cases. The first case is for fixed angle, and then the second case, which is more interesting, is the angle averaged interaction. So let's do the fixed angle first. So the complexity of these interactions goes up very quickly, because now if you have two molecules with permanent dipole moments, right, you can adjust the angle, the relative angle of the two dipole moments, one with respect to the other. And then in addition, you can twist one dipole moment with respect to another. So now there's four variables that have to be taken into account. Well, if you're worried about just about angles, now there's three angles, and then also the separation gives you the fourth variable. So Z is the separation between the molecules. You've got two orientation angles, theta 1 and theta 2, and then you've got this twist angle phi, which gives you four parameters that you have to take into account. The interaction potential energy is derived by referring to the interaction potential energy between a dipole and an electric field. Back in lecture 2, we derived that as just P dot E with a negative sign in front of it. The trick here is now that the electric field E that appears in that interaction potential energy, that electric field is the electric field due to a dipole, right? And the electric field due to a dipole, I've got written out in vector form in the second line of this equation. This is a standard result from electrostatics, second year electrostatics course in any standard university curriculum. So you'll find that equation written in many textbooks. The interaction potential energy is then taken by the dot product of the dipole moment P2 into the dipole electric field E. The dipole electric field E is produced by molecule 1. The dipole moment that's interacting with that is the dipole moment associated with molecule 2. It's P2. And when you work out all that arithmetic, right, you end up with this very complicated expression that has functions of cosines and sines in it to take into account the orientations of these different angles. And most importantly, you acquire a 1 over z cubed dependence. So the way I like to look at this is that complicated expression that involves all the sines and cosines, that can be represented by some function, f, which is a function of theta 1, theta 2, and phi, right? You've then got the dipole moments P1 and P2 multiplied by this 1 over z cubed dependence that describes the separation of these dipole moments, one with respect to another. Now, if you look at that red function of theta 1, theta 2, and phi, if you look at that carefully, it's basically a function that varies between -2 and +2. Just depends on which value of parameters that you choose to pick for the angles. And it's kind of interesting to realize that if the dipoles are oriented in their most favorable orientation, then that function of theta 1, theta 2, and phi acquires the value -2. And when it acquires that value, then the interaction potential energy between these two dipole moments is just -2 times the product of the dipole moments times the standard factor 1 over 4 pi epsilon naught times kappa, dielectric constant that these molecules are embedded in, times a 1 over z cubed spatial dependence. So that's the key result that we want to keep track of, right? Again, that complicated function of theta 1, theta 2, and phi, that's just telling you that the interaction potential energy between these dipoles is going to depend in a very sensitive way on how the dipoles are oriented, right? And so I give a couple, 3 examples here where I show you the orientation of the dipole moments where the interaction potential energy is a minimum, where it's a maximum, and also where the interaction potential energy is 0, right? Just to give you some physical feeling for what that function is trying to represent. If you take the time to do a 3-dimensional plot of that function, you'll end up with plots that look something like the 2 I've given here. These plots are a function of this parameter f of theta 1, theta 2, and phi. I've treated theta 1 and theta 2 as continuous variables, and I've picked the twist angle phi to be 2 extremes. One extreme is phi equal to 0. That's when the 2 dipole moments lie in the same plane. Their orientation is free to assume any angle orientation that you care to. That's shown on the plot on the left. The plot on the right is the result when dipole 2 is oriented at 90 degrees with respect to dipole 1. And what these plots show you is, first of all, they show you how this function f varies between -2 and +2. That's indicated by the color of the plots. So for those angles, theta 1 and theta 2, that are indicated by white on this diagram, that indicates an unfavorable orientation of the dipole moments. For angles theta 1 and theta 2 that are indicated by dark black on this diagram, those are favorable orientations, energetically favorable orientations of the dipole one with respect to another. And so you can see that if the dipole moments are free to move around on their own, and if the thermal energy of the problem is low enough, you can see how the dipole moments can get locked into certain orientations which are dependent on the wells, these dark black wells that are indicated in these plots, right? And of course, that's interesting, especially if the thermal energy is low enough, because it predicts ordering of dipole moments just because of these dipole-dipole interactions. Another way to build confidence in your understanding of how the two dipoles interact, one with respect to another, is to consider this simple situation that I've calculated in this particular slide. Here what I do is I consider two dipoles spaced a distance apart. The separation between the dipoles is indicated by the parameter D. The relative separation between the dipoles is indicated by the parameter S. And in this particular calculation, what I've done is I fixed the dipole on the right. I do not allow it to rotate, but I allow the dipole on the left to rotate freely through any angle phi that I choose. And I just use the formulas that I gave on the previous slide to calculate the interaction potential energy of these two dipoles as a function of the orientation of one with respect to the other. And I've got three situations here for different ratios of the parameters D over S. When D over S is a small number, that means basically that the dipoles are separated far from one another. And when that case arises, for instance, the case D over S equals 0.3 in this slide, you can see that the interaction potential energy just has a very shallow minimum, indicating that the interaction between these dipole moments when they're far apart is small. But when D over S approaches unity, that means that the dipole moments start to come up close to one another. So I do the case D over S as 0.75. And you can see very clearly there's a very sharp minimum, which indicates that these dipole moments, if left to seek their minimum in energy, right, those dipole moments would all tend to align parallel to one another. And let's say a dipole moment starts at some arbitrary angle, oriented at an angle of about, let's say, 160 degrees, one with respect to another. Your interaction potential energy would be indicated by this positive, this plus data point. And very quickly, if the dipoles can fluctuate slightly, they would tend to align, and they would assume an orientation parallel one to the other. So these are just simple examples, in plane dipole moments that allow you to maybe build some intuition about how dipole-dipole interactions take place. Again, the situation for fixed dipole moments is not terribly interesting in the context of this discussion. It's actually more interesting to consider the angle average, the thermal angle average of the dipole moments. And we have to rely back on the discussion that was given in the previous lecture on how to perform that angle average. And now we have to angle average over theta 1, theta 2, and phi. So the calculation is even more complicated than the one that we did in the prior lecture. Again, I work out the complete derivation in Appendix A for those of you that are interested in the math details. And what I do here is I just quote the standard result that was obtained by Keesom in 1920, in the early 1920s, when he considered this problem, right? He was the first person that worked this derivation out, and the interaction potential energy between two permanent dipole moments where the angles between the dipole moments are allowed to fluctuate due to thermal energy. Okay, the answer to that question is, what is the interaction potential energy? The answer is given by minus 2/3 1 over K Boltzmann times T times the product of the dipole moments P1, P2 squared. And now we pick up a 1 over Z to the 6th dependence. So the interaction potential energy now is going to depend on the 6th power of the separation between these two permanent dipole moments. So if you've been following along the lectures, what we're showing is that every time you make the situation a little bit more complicated, right? You go from point ions interacting, which is a 1 over Z. You start to put ion dipole moments in and allow them to interact. Then you go to, in this case, dipole moments. You go from a 1 over Z to a 1 over Z to the 6th, right? Which means that this interaction is very short range compared to the long range interaction between point charges. In the literature, all these constants in front of the 1 over Z to the 6th, it's often referred to as just one parameter, capital C sub K. K is for Keesom. And it's often very difficult to obtain realistic values for the dipole moments P1 and P2 for a material of interest in your situation. So the parameters start to be lumped together, and you've just now got one constant C sub K that describes this Keesom interaction. In this diagram, I just put in some numbers just to give you a sense of what the interaction potential energy might be for two dipoles. Again, I picked the case of an ethanol molecule. I separate the two ethanol molecules by 2 nanometers. These molecules have permanent dipole moments. 1.7 dBi is given in the table. And I just go through and evaluate the expression for the Keesom interaction potential energy. And I get a negative sign, which indicates that there would be a net attractive interaction between these molecules. But the size of the interaction now is really rather small. It's about 10 to the minus 10 electron volts. So it's down orders of magnitude from the interactions that we considered in the previous lecture. So any interaction that we've already considered previously would dominate this particular interaction, but all the other prior interactions involved interactions between a point charge and a dipole moment, basically. And if you don't have point charges floating around, then all those other interactions go to 0, and this becomes the dominant one, right? So that's why this is relevant to the case of atomic force microscopy, because usually your tips and your substrates are electrically neutral. The only interaction that's left over is interactions between dipole moments in the tip and the substrate, and this is one of the possibilities that could arise. The next logical point of discussion in this topic is to consider what happens if a molecule that has a permanent dipole moment interacts with a molecule that's nonpolar, that has no dipole moment. And again, you might think that there would be no net interaction between these two entities, right? Because the dipole moment of the nonpolar molecule is 0. But the electric field produced by the dipole, the molecule with the permanent dipole, that electric field can interact with the nonpolar molecule, and it can induce a dipole moment in that nonpolar molecule. And how much of a dipole moment's induced in that nonpolar molecule is going to be determined by the polarizability alpha 0, 2 of that nonpolar molecule, right? So if that nonpolar molecule has a non-zero polarizability, there will be a dipole moment induced in it. Basically, the electronic cloud of the nonpolar molecule will be slightly distorted. The distortion will take place in the direction of the electric field produced by the molecule with the permanent dipole moment. And I've tried to indicate that by this orange-colored oval in the diagram to the left of this slide, right? That's the induced dipole moment that's produced in the nonpolar molecule by the electric field that's generated by the dipole moment of the polar molecule. So these calculations just get more complicated. You have to have an expression now for the electric field produced by a permanent dipole, and the expression for the electric field produced by a permanent dipole, again, is a formula that's derived in your second class of electricity, of electrostatics. It's often not found in the introductory physics classes, but in your second electrostatics course, you should have derived this formula. This formula involves the angles that the dipole moment makes with the nonpolar molecule, and that angle is indicated by theta in this diagram. The strength of the electric dipole, the strength of the electric field produced by the polar molecule with a permanent dipole moment P1, the strength varies as 1 over z cubed. Now, so the further away the nonpolar molecule becomes, right, the electric field that it feels goes down as 1 over z cubed. Turns out that's an important factor, right? And if you calculate the interaction potential energy now between the polar molecule and the nonpolar molecule, the interaction potential energy is referred to as the Debye interaction, and the answer that you get for the Debye interaction is indicated on the right-hand side of this slide. The significant point here is that this interaction potential energy also varies as 1 over z to the 6th. So as the separation between these molecules varies, this interaction potential energy decreases rapidly, 1 over z to the 6th power of the separation distance. The answer, not surprisingly, depends on the polarizability of the second molecule. That figures prominently in the formula. Okay. So I think in this case, I just show how you obtain the formula. So the arithmetic here is pretty simple. You just have to do an angle average over one angle, and that's the angle average over theta, and that was shown in the appendix of lecture 4 to be equal to 1/3, so you can refer back to the appendix of lecture 4 to see how that factor of 1/3 comes in, and that gives the Debye interaction potential energy that I've got written down. Okay, it's a standard result. You'll find that in all the textbooks and review articles. It's interesting to consider replacing the nonpolar molecule with a polar molecule, right? So the nonpolar molecule in the previous discussion is now replaced by a polar molecule. And this second molecule, which is polar, could also induce a dipole moment in molecule number 1, right? So that also has to be considered, and if you have the case where you have two polar molecules that are identical, and each polar molecule has a polarizability, then it's possible that the Debye interaction can be rewritten, and the expression that you tend to find in the review articles is given on the bottom of this slide. It's a 1 over z to the 6th. If the two molecules are identical, then it's a p squared over polarizability in the numerator that determines the interaction, the Debye interaction between two polar molecules. So I think that's all I have time to talk about right now for these Debye and Keesom interactions. The Debye interaction is reasonably straightforward if you think it through. The arithmetic isn't too terribly complicated. The Keesom interaction involves a few pages of algebra. It's a little bit more complicated, but these are standard formulas that you find in all the textbooks. the derivations are often not given, just the final answers are stated. And so what I've tried to do is provide you with a little bit of physical motivation for where these formulas come from, and then I also provide the derivation of the formulas for you to look at. So thanks for listening to this lecture. This was probably the most complicated lecture of the 5 so far. The next topic is going to be the London dispersion force. This is going to describe how two nonpolar molecules interact, one with respect to another. And once we finish the discussion of that, then we'll move on to tip-substrate interactions, which is what I'm sure most of you are most interested in. So thanks a lot. You have to look at these notes carefully if you want to understand them. But I think it's worth the effort, because the more you understand about these forces at a fundamental level, I think the better off you're going to be when it comes to tips interacting with substrates. So stick with it, give it your best.